Hello everyone, welcome back. In this part of the tutorial, we will begin working out the small details of our Helix Bridge. On my screen, you should see where we're going to be tackling today. Mainly the opening that you see here. For example, as you can see, where it extends to a viewing part, this direction, you can see that the helices are cut because normally you expect this one to go down and down, down, down. And what I've drawn here is actually this part right there. This is the helix that was cut because it would normally go down. And this is the other major helix. Now, we have to find a way to make our model as parametric as possible so that where we place our viewing part, we will have this sort of counter section inserted, and the same will go for the minor helix, obviously, because it will have to be cut also. I don't think you can see it on my screen. This is one of the next minor helix that isn't cut, but the one before is actually cut. But you fortunately cannot see it on my screen. But what you can see is this part, this beam here. This is actually the counter section for the minor helix, because this is the one that I've drawn here, and this is the one that connects this one with the previous one that is off screen, that's off my photo. So that's what we're going to be tackling today. It's going to be a lot of fun, to work with these, because I've actually employed some tricks that I usually don't use myself, so that will be nice to show you also. The reason why we're trying to do this in parametric is because, one, since we are working in Grasshopper, we want to make it as parametric as possible. The second is it actually benefits us in terms of the next step that we have to do, which are these rods here that we have to make in the latter part of the tutorial series. So in terms of progress of the overall tutorial, I would say that we're more than halfway. The only thing we still need to do is, like I've explained, modifying our helices to accommodate any openings for the viewing part. The next step is probably going to be tackling these supports themselves. In terms of the covering that you see here, the glass and the mesh, I have not included that in this original tutorial, so perhaps I can pick it up on maybe a revisited version of this tutorial. So we'll see about that. And I think we can top it off with modeling these glass balustrades, so that you can actually use your model for render or for any purposes. Alright, with enough talking, let's get on to it. This is where we left off from our previous video. We have completed the viewing part entirely, so that part is done. Now we have to find a way to make this happen, or find a way to determine which helix we have to modify. So the theory goes, or at least the approach is, let's use the geometry that we have for our deck as some sort of like checking tool, to find which of these helix intersects with one of our viewing part, and where it intersects, we want to extract out that helix and cut it, basically cut this part and rejoin them basically with that part cut, and then rebuild the curve afterwards, and then find a way to make that point join up with that point over there. So that's our approach. So let's get on to it. So first thing we need, that geometry. I think we can find it. I think maybe this one. I don't want to do the whole bridge. I just want that part. I remember it came from a rectangle, was it? Or was it from a polyline actually? Well, definitely not that. Ah, then it's this one. Okay. Polyline. And then we extruded it up. Or was it extruded down? Doesn't really matter. We extruded that, I think, up. Yeah, okay. Okay. But let's extract that out first, so that we have it. What can we call this? We're gonna call this Boolean geometry. Because I call it Boolean geometry because we are going to be using Boolean operation to check whether it intersects or not. So let's put that here and make it hidden. Obviously, the next step is going to be needing the data from our outer helix or the major helix, whichever you want to call it. Not sure if you want the curve. I would prefer the points because intersecting a geometry with a curve can work, but ultimately what we want to do is we want the point data, because that's, if we have the point, which are these, we can make up our we can rebuild our curve. So let's go for the source. I'm gonna make another component. Let's just call it point and do the same thing here, and then we can what's this called? But instead of curve, it's points. We are going to add that here and then make a sort of outlet for us to copy. Okay, I can copy that and paste it here. Alright, so now we have to make our Boolean operation, make a Boolean geometry into a geometry itself, because now it's just a curve. So we're going to do a boundary surface, make it into a surface, and then we can extrude it up by let's just say by 0.1. Well, actually we're in millimeter here. The unit must have changed, so I have to change this back to meters. I think it must have changed back to that when my Rhino crashed. But so what is this 0.1 meters? It doesn't really matter that much how much you have here. But the important thing is that you just need a geometry, to test a solid geometry, and this is the way to do it. And one thing you have to take note is if you look at our front view here, like this is our geometry, and the point we want to test sits right on the edge of it. And just to be sure, what I like to do is move this geometry actually back down by half the extrusion height. So what I mean by that, if you connect this here, you move it up, but if you were to edit the expression and say minus because we want to move it down, half of its extrusion. And what you get is that the extruded geometry will move halfway down so that your point sits right inside, in the middle, in fact, of your geometry that you want to test. And that should give us a more reliable results instead of relying on, oh, does Rhino will it include the ones that's sitting on the edge or not? And now the main component we use for that is actually called point in VReps. Now there are two of these, and you can find it under surfaces and analysis. We have point in VRep singular and point in VReps, which it can look for more than one VReps, which is what we have since we have 4. So make sure you get the correct one. In terms of icon, it has a little plus icon, and the other one simply just doesn't have it. So make sure you have the correct one, otherwise you might not get the same results as me. It has 3 inputs: the VReps himself, and the point, and this is that strict Boolean that I was talking about, but I would rather not rely on it than just move. It doesn't cost you that much computational power just to move your geometry back down a little bit in order for you to get a better result. So let's connect these two together. I'm now seeing an error that we might encounter, and that's because we have 4 branches that will act only upon the first 4 branches here. So that's not going to give us a correct answer, and that's not what we want. Also, we want to test all points for all the Boolean inclusions. So what we're going to do is we can actually flatten this, and that will make sure that each and every of these branches will be tested against all 4 B-reps. The result could be messy, but it will give us the result that we expected to have. So let's try and see what we get by using a culling pattern on the points that we just used for testing. This is the true-false value, the booleans, and this is the index where it's inside or not. It's basically what we're not going to be using that one. So if you plug that in, what we expect is to see 4 points, 4 locally defined values. That's it. That's what we want. These are the 4 points. Exactly what we expected. And we can also see that only 2 helix actually intersects with our viewing part, which is quite interesting. Okay. So what we can do with this data is now we know which point that intersect, but we also, I briefly just mentioned, we can see which helix intersects with it. If you look at the list, branch number 0 and branch number 5 are actually the helices that intersects with it. So what you can do is, let's say you do an interpolate, because this is exactly how we built up our previous helix here, which is also using interpolate. So if you apply that, and now you have all these helices. You can flatten them, or you can use a tree branch. It's the same thing. Let's use a list item instead then, because we only have 1 branch per item, so it doesn't make sense to, well, it makes sense, but it doesn't matter. So let's say we know that 5, index number 5, sits, it's one of the helices that intersects, because you can see 5 has 2 elements, 2 intersecting points. If we do that, and voila, and 0 is that one which intersects there, and oh, okay, so the first 2 intersects with the first helix, and number 5 intersects with the last 2 in our case. Okay, that's nice to know. One way we can use, we can sort of extract these 2 helices and work on them and leave the others alone, because the others doesn't have anything to do with this intersection, so we can leave those alone. And what we can do with this data is actually identify which one we want to extract from it. So let's see, how are we going to do that? We can actually use a dispatch, because we can see we have data here, where actually we can use this instead, by means of converting true false values into numbers, because we know false is 0 and true is 1. Oh, this is a list that you really don't. Okay. And if you were to do a mass addition, what you will get is the list, or the helices that's not intersect with our viewing parts, will be having a mass addition value of 0, because, well, they never had a true in them. And that's to be seen in this list. This one has 2, because we know there are 2 points that intersects there. So what I want to do with this is actually use it in a dispatch. A dispatch basically sends items to either A or B depending on the true-false pattern. And what we can do with this, we can actually use the whole point list perhaps. to dispatch it already, so we don't need that for now. We do need the dispatch somewhere there, and what we want to do, we're going to keep that because we might need that. We might want to see where are the points intersecting, and now we can actually say let's do an evaluate, and our evaluation basically say if x is more than 0, if x is more than 0, then true maybe, or false. Doesn't matter which one you begin first, because we will get one value or the other dispatched to their respective places. So if you were to put a there, and then what you will get is, what's A? A are the ones that are intersecting. As you can see, 0 and 5, branch 0 and 5 has items, and the other ones just go to the B. And what neat about this, it actually retain our list of order, or actually our tree of order. Something that we can re-merge back again, and then we have that same order for us. So now we've identified which of these helix intersects, and we've isolated the ones that are not affected by it into a separate list, so we can work on that separately. So now what we can do is the points that intersects, we can find out which point it is within the points of the curve, within these A and B's. So what we're gonna do is we're gonna say point closest to point. Actually, point closest to another point. I think this is the one we can use. The point that we want to test is obviously this one, which goes into the cloud. The point we want to search goes into the P. And let's see, what do we have? We have two closest points and their respective indices. These indices are the points that you can find on the A list, basically. If you were to go into 48 on the first branch, you will find, I think, either one of these points that intersect. So now that we've isolated that, we can select it. But first, if you actually look, let's look back to our picture. Maybe that one doesn't help. Let me see if I can have another one. Let's see, I think perhaps this one can help. Let's zoom in there. So this is a viewing part, right? And I'm not sure if you can notice that, but the way that the points that it cuts from a major helix is actually 3 points, 3 sections instead. So if you were to see, this is roughly the same height. You can see that it actually stops here, meaning we have to cut off 1 point, 2 point, and the third that just stops there. So we need to cut off 2 sections that spans over 3 points. So let's put that back and continue with the script. So we need to find the first 3 points in order to isolate the first 2 sections. Okay, so in our example, what we expect is we expect that part to go, and this part to go, and this part will have to be in another way connected to that. But that's for the other videos, or actually in the next part we're going to tackle that. We're going to rebuild it. First we need to isolate it. First we need to make the cut, and then we repair it, sort of way. Okay, with that said, let's see, what can we do here? We have the indices. We can just say series, and the series starts with whatever index we have here, and the amount to cut is actually 3. because we need the first 3 points. And then we can say mm, then we can say points to remove. And that goes into the C, which is the amount to remove. And now what we have is a list of indices that we want to remove. Now the problem here becomes, now it begins to further branch out our tree, but we don't want that, because the first two actually belongs to the same curve. So what we can do is we can trim the tree back down into this. So now what we can do is we will have points which correspond to the index that needs to be removed, or the section between them at least. One thing we can do is we can start with let's rebuilding a curve, interpolate from this. Okay, it's red because we are also taking branches that has no items. So what we can do is we can clean the tree using the clean tree command. The n removes the null, the x removes the invalid items, I believe, and the x removes the empty branches, which you want to set to true. There we go. The nice thing about this actually is that it maintains your data structure. So as you can see, branch 0 and 5, so it maintained that. And now if you plug this in, you should have a nice green or light gray component if you don't want to see the red. Okay, so with that gone, what we can do is we use the indices that we found as points from, actually we can come from here now because that tree is now cleaned, although this is not clean, so we might have to clean both, or we just don't do it yet, which maybe is a wiser thing to do. And that way we maintain it. So we have these points instead. Okay, I can see a problem already. We don't want those points at the bottom. We actually want the ones that are on top. That's the one we want to call. That's the one we want to break, right? So this is one of the issues where using this method is fine, but we still need to tweak this a bit in order to make the script more reliable. And one way we can do that is by saying, let's always get the indices that are coming to this direction, let's say in the positive z direction. In that way you can always get it, because you can see here is wrong, here is also wrong, there is also wrong, there's also wrong. Okay, so looking at this, you might say, okay, why not we just flip the order of the list, which you can do, of course, which is here actually. If you do this -1, it will count the other way, and then you have the correct ones. Yes, that could work, but what if you have two curves that are not in the same direction, or if you don't know the direction of your curve? Well, actually, the curves are built from the same way, so they should be all looking at the same direction. The only problem you may encounter is actually if you if you copy this whole method into the inner helices. So if you actually know that we need to modify that, what we can do is let's move. This is actually an operation that we can move to a later state. So we have to do a modification here. What I suggest we can do is say, let's do a list item. Let's get, where do these come from? These come from these points. And now I'm selecting the same, but let's say x plus 1. Let's say the next one. So now we have 2 points we can use for comparison. for that. And what we want to do is let's do an evaluate. And in this evaluate, we want to say if the first point, the x of the first point is higher than the x of the second point, that means it should be flipped, then it's -1, otherwise it's 1. So the first point meaning this one, the second point meaning that one. There's an error, point or vector. Let's try copying this way and see what the error actually is. No error. What? That's kind of weird. Oh, because we are using empty branches. Okay, I see. So we need to clean our tree a bit. Where should we start cleaning them? Should we clean them here or here? I would say let's do this instead. Let's clean these two. Therefore, we have two nice curves. We still have. Oh, this one should come from this, and that is now green. Okay. So we've cleaned our tree before we do any operation. Apparently, this evaluate doesn't like those kind of options. Okay. Now that we have that, we only actually need one of these numbers. We don't need both numbers. Because what this come out is actually, I'm curious what we get actually. Let's see. This is, oh, we have a list there already. This list is null. Oh, because it's still coming from the other one, so we can use this one instead. Let's use this one. Let's copy this one here instead because I want to see. If this one was set to 1 as a default value, and everything will change back, and then we flip the tree. Okay. Well, apparently this is the trick that we want to employ, and what we should get is the same 3 above, the same 3 above, the same 3 above, the same 3 above. The next step is, now that we have the points that should be called, we can say point closest to curve because we want to have the t parameter because we want to shatter our curve. So all this is actually to find the points that is actually on, well, they are on the curve because that's where they come from. But what we don't know is what are the parameters on those points. That's what we do all this to identify it. First thing is to identify which are the points that we need on which index. The second is to find out I want all the points on the z-axis, so above the deck and not under the deck, in case it does that. So we can actually use this method for any type of helix, and you always get the top one. The curve being this one, obviously. This one will go here. So these apparently are the parameters. Okay. And then we're going to shatter our curve. Let's do this. And now we should have, let's see, 7 curve. Well, there's always 2 being shattered. That could make sense. Or actually, what we can also do is for the parameters, we only need the first and the last, to be honest. Oh wait, that's not true. That's not true. Because we combined our list by trimming the tree. So let's keep it at this. What we can do, however, is let's sort this by length. And let me see. And then we can sort of delete the shortest curve because we know this part of the curve is going to be the shortest for sure. Okay, what can we come up with for a evaluation in order to do that? Well, let's sort this first. Numbers goes there, sortification goes here. Let's do that. This item should give us the first short curve. Okay. I have an idea. Why not just say, okay, I'm going to use this again. And why not just say, I want any curve that's shorter than this plus a tolerance that's a 0.1, 0.5, whatever, should be called, right? So you can say if x plus 0.2, 20 centimeters longer. Is that going to happen anywhere else in our script? No, that's not. So we can say x plus 2 is smaller than y. Then, wait, if the smallest curve is smaller than y, then you get called, I guess, and not is true. Let's test this and see what happens. I'm basically testing all the lengths of the curve to this curve number, this length, which should be, all the long curves should be longer than this, so this would equals to true, actually, or not. Wait, okay, let's see what happens. What's that? That's the length, so that one should go to x. And the length of all the other curve is actually that one, isn't it? We expect to see 2 branches with 7 values. Okay, and now we can say call pattern. That's the pattern we want to call, and this is the tree we want to modify. We can hide all that. Okay, so we have to flip the true and the false basically, because now we're only selecting the shortest curve, which we don't want. So let's come here and evaluate back why we changed that. Now we have the perfect one selected. As you can see, there's no curve here. So what we said is if the shortest length plus a tolerance is smaller than the length of the curve that we're going to test, that if that equals to true, it stays. Which makes sense, because the longer curve is always going to be longer, meaning the shortest curve plus the tolerance is always going to be smaller than our longest curve, but the smaller ones is not. So this actually evaluates to true when we want to keep the ones that we want, the longest curve, and that is the first condition. If it values to true, it will keep it, meaning the true. If it values to false, it will just delete it, which is the false here. But if you don't understand this, it's basically a 50% chance. So if this doesn't work, you just flip one of the true false value and you will get the other results. It's quite easy to do that. And if you need more time to understand this, please do take that time to understand, because this is quite important. And somewhere we still have points. Where? Oh, here. So we don't need to see that, actually. All right, let's zoom back out a bit and see if we really done our job. That one is okay, that one's okay, and that one is okay, and so is that one. Perfect. We have successfully modified our curve in order to accommodate any viewport positions. Okay, I think this has been a lengthy tutorial up to now, so we're gonna stop this here. Actually, you know what I'm gonna do? I'm going to do I need to see this? I don't think I need to see it, so I'm gonna copy this because we're actually rebuilding our curve. So we can do is let's merge. What's this? These are the curve. Okay. Let's remerge our curve. I think it maintains the list of order. That's fine. With the original ones, we might have to flatten some of these. I don't know which one. Oh wait, those are points. We don't want points. Oh, we forgot to clean this. We need to clean this also. And give it a nice rebuild. I think one of them might have to be, yeah, we have to simplify this one so that the tree structure matches up nicely. Okay. We might need to copy the diameter of the tubes because we're using it from the other one, which is fine, but to keep our groups clean, let's just keep to this. And I should be able to disable that, and then we don't actually want this one here anymore. Is this rounded? Oh, it's open. We want it rounded actually. There we go. The first hole in all the major helices. Okay. I'm gonna stop the video here, and in the next part we are going to tackle basically doing the same, or actually no. In the next part we're going to finish up with our major helix and connect into 3 points. The first being find a way to connect it to that point. We have to find a way to see which point that is. I believe it's in the middle of that one, and also connect it here because now we've broken that part. And I believe it also has to connect here or something. Yeah. So there are 3 things we need to tackle. Actually, yeah, 3 things. 1, 2, and 3. And we're going to take that up in the next parts of the video. Thank you for watching, and I'll see you in the next one.